because our test is next week, Tuesday. So that is coming up quick. Chapter 2 is a short one. And today has to deal with this idea of modeling quadratic functions. Back in chapter 1, we worked with modeling linear functions. We had these tables that often, not always, but often somewhat looked linear. And therefore we said they had a correlation, and we could write an equation of fit for that. But that was just for linear. The thing is, you can do that for any type of equation. If it looks somewhat quadratic, you can make a quadratic equation that somewhat fits that equation. If it looks like it's exponential, you can make a line of fit that is exponential. And we could do this for every type of function. And so that's what we're going to be focusing in on today. Now, a little bit before we get there, we're going to talk about just being able to identify what type of function you have based on looking at a table. If you have a table that is, and we're going to focus in on linear, quadratic, or exponential for those three types that we're going to see today. If you're going to have one that focuses on one of these three, then the table itself is going to show some things consistently. Assuming, of course, that the x values are equally spaced. So like these ones, all the x's are 2 apart, all the x's are 1 apart, all the x's are 1 apart. And if you have that, you should be able to see what type of equation it is based on looking at the differences in the y values. Linear functions have what's known as a first difference that is the same from step to step. So as if your x values are equally spaced, then your y values, how you get from one to the next, to the next, to the next, to the next, should all be the same. Like here. Since my x values are equally spaced, how do you get from 15 to get to 20? Add 5. How do you get from 20 to 25? Add 5. 25 to 30 is adding 5. 30 to 35 is adding 5. This is that first difference. And since all of these are the same, that's linear. It's perfectly linear, not just somewhat linear, it's perfectly linear. Quadratic graphs don't do the same thing. A quadratic function will have a second difference that is the same from time to time. And the second difference, essentially you look at your first differences and you see how they change. Exponential functions are very different. Exponential functions will not have a difference that is ever the same. Instead, you will be multiplying by the same number from term to term. So if I want to determine if I have a linear, a quadratic, or an exponential table, I check that my x's are evenly spaced, and I start looking at the differences. Sometimes it's going to be obvious that the first difference is not the same, or that it is. The first difference should be pretty easy to see. Right here, pretty clear we're not adding the same thing from term to term, right? Because like here I'm adding 6, here I'm adding, brain shut down, 24. Here I'm adding 1.5, and here, notice I skipped over it. If you're trying to figure out what you're adding, you can always work backwards with ones that are not obvious. If I wanted to figure out what I was adding to get from 8 to 32, I could have done 32 minus 8, and that would have given me the 24. I could do the same thing with the fractions. 1/2 minus 1/8 is 0.375. Since the first differences are not the same, it's not linear. I can check the second differences. To get from here to here, 1.5 minus 0.375 helps if you type it in right. Adding 1.125. To get from 1.5 to 6, are you adding 1.125? No, which means the second differences are not going to be the same either, which means it's not quadratic. Get from here to here. I don't really need to check anymore because of the fact that they're obviously not the same, but it'd be adding AT. First difference is not the same, it's not linear. Second difference is not the same, it's not quadratic. Am I multiplying by the same number to get from term to term? If the fractions mess with you, don't look at them first. How do you get from 2 to 8 by multiplying? Times 4. Is 8 times 4 32? Okay, then go to your calculator. 1/8 times 4, is that 1/2? If I multiply by 4, am I getting 2? So, that's exponential. Okay, we got one more here. My x's are evenly spaced. How do I go from 9 to 4? Add your subtracting. Subtracting 5. How do I go from 4 to 1? Subtract 3. From 1 to 0? Minus 1. Plus 1. Plus 3. Plus 5. They are not all the same. What does that mean? Check the second difference because it means it is not linear. How do you get from -5 to -3? Add 2. It's getting less negative. Be careful. How do you get from -3 to -1? Add 2. From -1 to 1? Plus 2. Is this plus 2? Plus 2. Second differences are all the same. That means this is quadratic. Downside to this, it only works if it's perfectly linear or perfectly exponential or perfectly quadratic. Doesn't work for those ones that kind of look linear, kind of look quadratic. Remember back in chapter 1, I gave you some graphs that kind of looked like this? Said there was a strong correlation, positive correlation since it was going upwards. That can happen with the other forms as well, which is what we're going to focus on back. To deal with this, we went to the graphing calculators. If we wanted to write a function that approximated a linear regression, what was the first thing we had to do with the numbers in the table? Put them into the calculator. On the TIs, where do I put them in? stat. And then we edited the lists. By the way, I am not on this test going to give you the hints on that direction. So if you do not remember how to do this, you're going to probably want to write things down, whether it be here or whether you write it in the notebook to remember your steps. On the TI, again, stat, and then we went into edit. On the Casios, where'd you have to go? You get to make a note card. You go back to your main menu on the Casio, and then you have to go into statistics, where it gives you the ability to type in the tables. Ooh. Got stuff there. Make sure you're getting rid of it. List 1 is your typically X values. In general, it's the input. In this case, it's the time. Y values go into list 2. From here, we typically wanted to check if it actually looked linear or not. Now, that's going to be more important because sometimes it's going to look linear, sometimes it's going to look quadratic. Linear looks like a line, quadratic looks like a parabola, like a U shape, either upwards or downwards. So we want to see our graph. On the TIs, we have to have our stat plot turned on. Now our stat plot should already be set up to do a scatter plot. If I go second and into stat plot, it looks like a little scatter plot there, and it even tells me what lists it's using. Mine's using list 3 and list 4, which is a problem. I wanted to say list 1 and list 2. Yours probably doesn't have that issue. But it probably says it's turned off. In stat plot, you can go in there and turn it on, or if it's easier, and most of the time it is, on a TI, if you go into y equals, you're going to have to get rid of these equations anyway, if there are any. Do you notice that my plot 1 is highlighted? If it's not, I can go up there and click enter and highlight it, and then it'll turn it on. From there, I want to look at the graph. Now, I can click graph, but the graph isn't necessarily going to show me the right part of the window. It might show me right here on the graph instead of the big picture. On a TI, click zoom. Yep, that's what I'm talking about right now. So, click zoom. Click clear to get out of the issue, and then click zoom.
What am I zooming in on if I'm not in the graph?
I'm gonna show you.
Oh, okay.
You do zoom stat, and it will zoom in on where the statistics are. And then it should show you the graph. Once you click zoom stat, the TI will show you the graph automatically. Elsie, did that fix the problem?
Yeah, I think so.
Perfect. So You don't have to click the graph first to go to the zoom. So if it's easier for you to enter your statistics in the edit, go to the y equals to make sure plot is on, go directly to zoom and then statistics, it'll show you your graph. On the Casio, once you've got your stuff in, come on, bring back. Along that bottom row is where your menus are. I don't see graph right now, so I'm going to click F6 to move over. Yours might show graph. Mine doesn't. Graph. In theory, the first graph should already be set up to do all the things for plotting because we've done it before. Click graph and it already will show you what the graph looks like. The Casio, you don't have to tell it where to zoom in. Is there anyone who hasn't gotten to this point on their calculator? Does it look like either a line or a parabola? Looks like part of a U, right? It's cut off, but it's part of a U. It looks like a parabola, which means it's quadratic. Which means if I want to write a function, I don't want to write a linear regression. That's linear. I want to do a quadratic regression. So we've established it's quadratic. Now we want to do the regression. On the TI, go back into stat. Over to calculate. On the Casio, look at the bottom left corner of your graph. Do you notice it says calc right there? You could save yourself from some steps by just clicking that calc. It's calculating a regression. It knows you want a regression. We want a quadratic regression. TI users, can you guess which one's the quadratic regression? Probably the fifth one that says quadrag. Do I want to use list 1 and list 2? Absolutely. Yes, 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 yes. Just click enter until it shows up. On the Casio, which one of these looks quadratic? X squared is a quadratic feature. Click that one. It tells you A, B, C, and R squared. It also says y equals ax squared plus bx plus c to tell you where those numbers go in your equation. Y equals, instead of a, what am I writing? -11. It's easier to see this one. Don't forget the x squared plus bx. Instead of b, I'm writing 700x plus c plus 21,000. Notice it has an r squared on there. With linear regressions, we talked about the correlation coefficient r. R was very specific to linear. R squared is what you use for quadratic. You don't have to worry about r and r squared. We're not dealing with those. But it being 1 is telling me that this one wasn't just quadratic, it was actually perfectly quadratic. But there's my function for the height in terms of time. Now in all technicality, it wants t and h of t because those are the variables that it said to use. Am I going to get overly picky if you used x and y because that's what the calculator said? No. Technically, but yeah, I'm okay with that. Evaluate the function to approximate the height at which weightlessness occurs. Have we said anything about weightlessness yet? We probably need to go back and read the question. NASA can create a weightless environment by flying a plane in a parabolic path. Oh, hey, it even told you it was quadratic by telling you it's a parabolic graph. It means it's a parabola graph. Oops. The table shows the height h of t in feet of the plane t seconds after starting the flight path. After about 20.8 seconds, passengers begin to experience a weightless environment. That's the key piece of missing information, is this sentence right here. 20.8 seconds. Which variable is that? It's a time. So it's t, or if you used x and y, it's x. They're telling us t is 20.8. Now, I've said this many times in this class. If you have an equation and you have in this case it's a t value, how do you find the other value? Plug it in. Now, on the Casios, it sucks because you have to go all the way back to the run matrix. So back to your main menu, back to your run matrix to plug it in. On the TIs, I just clear out of this and it lets me plug it in. Negative 11, 20.8 squared plus 700 in parentheses 20.8 plus 21,000. Put the number you plug in parentheses. Nothing else goes in parentheses unless parentheses were already there. They weren't. For the sake of our notes, I'm going to write out what I did. $30,800.96 feet. Last thing that's on this question says find and interpret the y-intercept. What's true about every y-intercept? The x value is 0. Or in this case, it wasn't x and y. If I did the technical one, it's t is 0. Now, I'll tell you straight up, it's 21,000. That's the find. Now we have the interpret. 21,000, what units are on that? Feet. That's the number of feet when time is 0. In other words, it's the number of feet they started at. It's where they started making that parabolic path. You can write at the start, or even if you prefer to say when t equals 0. But that's what a y-intercept tells you. It tells you where to start. It tells you when a certain value is 0. The rest of the questions are really going to be similar. The difference that you're going to see is questions like question B. Use the model to approximate the best gas mileage. That's not looking for a y-intercept anymore. The best, what typically makes something the best? Gas mileage wouldn't be price. In general, it's the highest or the lowest of something depending upon what you're looking at. Best price, Lowest. Best gas mileage? Highest. Where's the highest point on a quadratic equation? What's it called? The vertex. It's looking for its vertex for the best gas mileage. At what point do they break even? It's talking about a number of students and profit. Breaking even means what? What's your profit when you break even? Zero. You don't lose money, you don't make money. It's telling me my profit's zero. It's telling me why y value equals 0. And it wants you to find the x value that associates with that. So, I'm actually not going to go fully through these two problems for our notes, because the process is the same, save for how you deal with the follow-up questions. And those are interpreting what it means for your situation. The key thing you're going to look at today is you're going to be entering data into your calculator, determining if it's linear or quadratic. You can determine if it's linear or quadratic depending upon if the graph looks something like that. If it looks something like that, is it linear or quadratic? Linear. If it looks something like this, it is quadratic. U shape is quadratic. Lines are linear. And then write an equation. If it's quadratic, you do a quadratic regression. Or, for those of you who are using the Casios, under the calculate and the regressions, quadratic is x squared. If it's a linear, you do a linear regression. On the TI, it says lin reg. On the Casio, linear is just regular x, and it would have been ax plus b. And that would have been the linear regression. That's what you're doing today.